So just to remind us what this lab was, we had a cart attached with a string attached to it, going over a pulley and a hanging mass off the end. So it was basically, it looked like this. So you had a cart with wheels on a track, and because it's got wheels, we can assume there's no friction. Now there is friction, but we're going to say the friction is negligible. Remember that fancy word? For it's there, but it's not enough to really be worth worrying about. So we're going to say that friction is negligible here. Then this came over here to a pulley, and it hung down to a hanging mass. Okay. And because this is connected by a string, when we let go of the hanging mass, the whole thing accelerates. Okay. So the first thing we want to do is think about what the force diagrams would look like for each individual object uh, when um, when we release it, right? Not when it's just hanging there, but after we let it go. Okay. So after we let it go, the hanging mass here, it would have FG down, and I'm going to call this object B and this object A for the sake of keeping it straight in our mind. So this is the FG of object B, and there's a tension force going up. Now, because it's accelerating downwards, we know that the FGB must be greater than the tension force, or it wouldn't accelerate in that direction. Okay. Now we go over to this one, and here we'd have FG down of box A, FGA, and we have a normal force up because it's on the track. Okay. And these are going to be equal to each other because it's not accelerating in the y direction at all. But there's a tension pulling it this way, right? And that tension isn't balanced by anything else because there's no friction. We're told that. You'll be told that. But we can assume because of the wheels, no friction. Okay, now the other thing we have to notice about our system here is that this string that's attached to B is the same string that's attached to A. And because of that, that means that the tension has to be the same all the way along that string. In other words, the tension force that's acting on block B over here is the same as the tension force acting on A. Let's not forget that, so let's tick mark it to make sure that we don't. So we have tick marks here. Okay. All right. So now let's get to the lab, to the understanding and what we're actually doing. So we're gathering data in the lab, and we're doing two different experiments. We're experimenting to see how if we change the system mass, okay, without changing the net force. So wait a second, net force. What is net force? See, what net force is the force that causes the acceleration, right? That's what net force is. Net force causes acceleration. Balance force means no net force. So since this is accelerating, we know there's a net force. And the question is, where's it coming from? What's causing this whole system to accelerate? And by a system, what I mean is box A and B together. See, because they're connected by a string, when I let go of the whole thing, both move and they both accelerate at the same rate. Now, I understand box B is going in one direction and A is going the other way. And that's okay. The pulley is the only reason that's happening. The pulley is changing the direction of the force. That's what pulleys do. Okay, so the whole system is accelerating, but because of what? Well, when we look at it carefully, we can say, well, which force? There's one force responsible for it. If we look at it carefully, we all can see that FGB, that's where the net force is coming from. Okay, FGB, in other words, the force of gravity, not the mass, the force of gravity on the hanging mass there is what's accelerating the system. So this is our net force, whatever the FG of the hanging mass is. So depending on how much we have there, like if we had 1 kilogram there, it would be 1 times 9.8 newtons per kilogram. That would be our FGB and therefore our net force. If it was a 2 kilogram mass hanging there, well, then it would be 2 kilograms times 9.8 newtons per kilogram. That'd be 19.6 newtons. That would be our net force. If we had 3, you could see whatever we had there, we just multiply it by 9.8 and we know what our net force is. Okay, so in the first experiment, what we did is we kept this the same. We kept this the same, and you got to choose whether you used a 1 kilogram, 2 kilogram, or 3 kilogram mass there. You could choose it, right? But you had to keep it the same for each trial. And we changed the system mass. And what that meant was, okay, how can we change the system mass? Well, the system mass is the mass of A plus B, right? System mass equals mass of A plus mass of B. That's the system mass. Mass A plus mass B, that says up there. It's in the glare, I'm sorry for that. It's hard to see. I've got this overhead light here. Okay, that's what our system mass is. And so if we're trying to change the system mass without changing the FG of B, the only thing we can do is add mass to the cart. Because then we keep the net force the same, but we change the system mass. So that's what you did. And when you did that, you gathered the data, and the data came in terms of distance and time. It didn't give you the acceleration. You had to calculate it. So if you're trying to do that and all you had was distance and time, you know that it's starting from a stop. So there's really only one equation that'll work, and that's this one. I'm going to write it way over here. It's the x minus x naught. It's this one, equals v naught t plus 1/2 at squared. And the reason that one works so good is because since it starts at a 0 velocity, this goes away. So you use your distance equals 1/2 a times time squared. And you got that data from the lab. That gave you your data points so you could graph. Okay, and you did that for both experiments. You had to do acceleration for both of them, and you couldn't measure the acceleration directly. Okay, so we go ahead and we could do that. Now the second experiment then, so if this is one of them, the other one was where we keep the system mass the same, but this time we change the net force. So if I keep the total the same, and I want to change this, the only way I can do that is to move some mass from the cart to here, right, for my trials. So, and you're only given the options of a 3 kilogram, 2 kilogram, or 1 kilogram mass, and the same 3 mass options for the cart. So really all you could do is like 3 kilograms here and 1 here. That gives you a total of 4, right? So you had to keep that total the same. So then you could go 2 here and 2 here, just to get 4, right, total. And then you could do 1 here and 3 down here. Can you see how you could get 3 trials out of this? That's what you should have done, and then graph that. Now, the graphs, let's look at what those will look like over here. So the first graph, and I want to do the second experiment. Let's do the one where we graphed net force versus acceleration. So when you did that, you'd have F net on this and acceleration here, and you got a linear graph. And when you wrote your equation then, y equals mx plus b equation, you have no y-intercept, so you can leave the y-intercept off. It's, think about it. If you had a 0 net force, in other words, nothing hanging here, what would the acceleration be? It'd be 0, right? So there's really no, it starts right at the 0 point. And that's how I would do it. Okay, so our equation then here is F net equals our slope, which you should have gotten to be 4 kilograms times A. Right? And that should have right away, 4 kilograms. That's what my system mass was. Oh. So in this case, the slope, which is this, That's system mass. Oops, system. Can't spell system. That's the system mass. Right? And that allows us to rewrite this equation, substituting in F net equals ma, but mass of the system, right? And because we use the whole system in our graph, we have to include the system mass in there. And our whole system was accelerating, therefore we can do it this way too, right? So this is our basic equation. Guess what? That's Newton's third law. And we'll see that in a second. But let's look at the other one we did. So now when we did mass versus acceleration, we got an inverse. So we had to linearize it. And you went through all the steps of linearizing. If you forgot, I'm sure you looked up the video that was posted before that told you how to do it again. You would have had to graph mass versus 1 over acceleration, and then it came out linear. So when you did that, depended on what you had hanging there, what you decide to make your F net, because this was the one where you had to keep F net the same for every trial. So if you use the smallest mass, you would have gotten mass equals, right, 9.8. And your units, look at this. Units is, watch what happens with the units. It's kilograms over 1 over meters per second squared. Right? Because 1 over A is 1 over meters per second squared. And so when you rearrange this, that equals kilograms times meters per second squared, which is newtons. That's a newton. So 9.8 newtons times 1 over A is your equation for that. So what is 9.8 newtons? Well, that was this. That was this, right? If that's 1 kilogram hanging there, isn't 1 times 9.8, 9.8? Yeah, it is. So basically, your slope in this one, that's your slope, that's F net. So now you can rewrite that equation, and you get M equals F net times 1 over A. It's the same thing. Well, it should be, because it's Newton's second law. Now, here's what Newton did, though. He didn't give it to us like that. Newton said, in terms of acceleration, what Newton said is that acceleration equals, right? He said that acceleration equals, not, he said that equals F net over M. That's what he said. And what he said was, he did it in words. He didn't write it as an equation, although he eventually did. He said that acceleration is directly proportionate to the net force and inversely proportionate to the mass. Okay, well, we see that here, inversely. Mass and acceleration are inversely proportionate, right? That's what Newton told us. What that helps us with, though, is this. See, because don't we write net force equations all the time? Don't we? Like when we do the sum of the x's or the sum of the y's, what are those? Those are net force equations. In other words, when we consider the forces acting on an object in two different directions and we add them together, that equals the net force. That equals the mass times the acceleration. And it always has, even in the last unit. It's just that the acceleration has always been 0, hasn't it? Because it was constant velocity or stopped, and those have 0 acceleration. So therefore, ma is 0, and we were writing equals 0 in all our equations. But it's always been mass times acceleration. And this is useful to us because now we can figure out what the acceleration is of an object. Since F net equals ma,